Hey Phys 1 kids, Campbell here. In this video, we're going to talk about Kirchhoff's rules and how to solve some circuit problems. Now, it's very important that you understand that a light bulb or a resistor or any circuit element cannot destroy electrons. They can't create electrons either. They can't store electrons, so that means the number of electrons that enter a device like a bulb or a resistor have to be equal to the number of electrons leaving the bulb or resistor or battery or whatever. And so that means that the current on either side of any circuit element has to be equal. This is actually dictated by the law of conservation of current, which is really like the law of conservation of charge. The current is the same at all points in a current carrying wire. So when I hook up a simple circuit with just a wire and a battery and maybe a bulb, the current everywhere in that circuit is the same, everywhere. Now, this leads to Kirchhoff's first rule, or sometimes they're called laws. I think I'm back the second one I call the law. And Kirchhoff's junction rule says the sum of the currents entering a junction, which is like a split in a wire, is equal to the sum of the currents leaving that junction. So I like to call it what goes in must come out. So if we take a look at here's a junction where I have 8 amps coming into the junction, so that means 8 amps have to come out. Now, if I had equal resistors on both sides, like maybe I had identical bulbs here on both sides of this, then it would be 4 amps and 4 amps. But obviously here, my resistors in the other parts of the wire must be different because I have 5 on one side and 3 on the other, but it doesn't matter as long as they add up to 8. So what goes in must go out. If I have current both coming in and from 2 different wires into a junction, again, what goes in must go out. So if I have 8 coming in, if I have 9 coming in, 8 plus 1, then I have 9 going out. And it doesn't matter, what dictates how much is in each branch is dictated by what elements, what resistors, what magnitudes the resistors are. But what goes into the branch for current must come out. What goes in must go out. That's the law of conservation of charge. There is another rule that has to do with energy. So if we think about the energy in a circuit, one of the ways that it's easy to think about current and circuits is to think about it in terms of like water going through a pipe, except we have electrons going through a wire. But if we think about water in a water wheel, right, when water goes through a water wheel, it turns that water wheel, it does work and changes the energy of the system. It's the same thing for a light bulb. What happens when current goes through a filament in a light bulb, I have friction, right? As those molecules, those electrons try to get through all those atoms. And that creates friction, right, which creates heat. And the wire gets so hot, these filaments have so much resistance that it starts to glow. Now, that means that energy gets lost in terms of thermal energy from the system. But it's not that the electrons are being destroyed, and it's not that we're losing energy to the whole world, right? It's just being transferred out into the environment. So if we think about the whole transfer of energy process, the energy transformations occurring in a simple circuit here with a battery and a bulb, I am starting with chemical energy for my battery. That becomes kinetic energy. When I connect a wire, the electrons start to flow, so that becomes kinetic energy. And that kinetic energy, when it gets to a resistor, generates thermal energy. And again, we say the thermal energy is dissipated, or the energy is dissipated as thermal energy. That means it's being lost to the system. Dissipated means it's going away. Not that it's, like I said, lost to the universe, but it's lost to the system. And so as an electron moves through a circuit, it gains energy at the battery, it loses energy at the resistors, so that the total sum of the energy change in the circuit is 0. And that brings us to Kirchhoff's loop law. Kirchhoff's loop law, or loop rule, says that the change in that voltage, or that electric potential around a closed loop, has to be 0. So what I gain at the battery, I always gain voltage at the battery. What I lose at the resistor that gets dissipated as thermal energy has to add to 0, because I can't be just creating energy in the circuit. So what I gain, I have to lose before I get to the battery. Otherwise, I have a net increase in energy. And that would violate the law of conservation of energy, although if we could do it, we should patent it. So if we look at just a simple circuit with a battery and a resistor, if I gain, say, 4 volts at the battery, it's a 4-volt battery, then I have to lose 4 volts at the resistor. If we throw another resistor in there, then I'm going to split the voltage from the battery between the 2 resistors. Now, if they're equal resistors, those will be equal voltage. They'd be like 2 and 2. Obviously, this one resistor here must be bigger because I'm dissipating more voltage. Remember that voltage by Ohm's law would be the current in the resistor times the resistance of the resistor. And if you think about it there's no junctions here, right? So the current has to be the same everywhere in this wire. Everywhere in the wire there is a steady current, and so if I have a higher resistor, I'll have a higher voltage drop, and which is what you can see in this picture here. Obviously this must be a bigger resistor here, and that's why I'm dissipating more, but it doesn't matter as long as they add up to 0. What I gain at the battery, I have to lose at the resistors. That's the law of conservation of energy. Let's take a look at a voltage graph of a circuit, because sometimes you will see these or have to draw them. So if we look at a voltage graph or a potential difference graph, and I start at point A, that's below this battery. As I move through the battery, right, I gain potential. I gain voltage till I get to B. And so this voltage amount is going to be the voltage of the battery, 1.5, 9, whatever the battery is. And then I get to my ideal wire where I don't lose any voltage because it has 0 resistance, right? So that's this little path right here. And then I get to my resistor. And when I get to the resistor 1, I'm going to lose some voltage. And you can see that right here with this drop in voltage. So as I move across the resistor, right, there's some distance. This is voltage versus distance in the circuit. I lose some voltage. And so maybe if this was like a 2-volt battery, this would be a loss of 1 volt because it looks like it's about half. And then I go through at my segment of ideal wire, and I hit the next resistor here where I'm going to lose some more voltage. And it looks like these must be equal resistors because these drops look the same. But the magnitude of the drop should reflect the magnitude of the voltage change across the resistor. And then I get back to 0 because I'm back to this ideal wire, and the voltage change around a closed loop, right? This is a closed loop, must be 0. We'll be drawing some more of those in class. Now let's look at how we use Kirchhoff's laws to solve circuit problems. The first thing, if you haven't been provided a diagram, draw one. A picture is worth 1,000 words when we're dealing with circuits. Always assign direction of the current so it comes from the positive terminal of the battery, because remember, we follow conventional current. Now, sometimes if you're doing more complicated problems, that may change, but for this class, we're always going to make the current come out of the positive terminal of the battery. And notice it goes all the way around this closed loop. So I have a closed loop where I have current flowing out of the battery through the resistor. Now, we always gain voltage at the battery when we draw current this way, and we always lose voltage at the resistor. So we're going to apply Kirchhoff's rule, which says the sum of the voltage have to equal 0. So the voltage at the battery plus the voltage of the resistor have to be 0. So I like to write it as VBAT minus V across the resistor, right? We're losing voltage there, equals 0, or that means that the voltage I gain at the battery has to equal the voltage I lost at the resistor. And I only have one resistor here, so they're going to be equal to each other, like in the previous slide where I had the 4 and 4. Now, we can use loop equations to solve for the current in the circuit by combining it with Ohm's law. So I had VBAT, right, minus V of the resistor equals 0, or VBAT is equal to VR. Now, the voltage at the resistor, if we go to current Ohm's law, the current through the resistor is equal to the voltage across the resistor divided by the resistance of the resistor. So if I rearrange this, right, I get the voltage of the resistor is equal to the current through the resistor, which is going to be the same as the current coming out of the battery because there's one loop, times the resistance of the resistor. So that means that VBAT is equal to the current at the resistor times the resistance of the resistor. So the current at the resistor in this case is equal to the voltage of the battery divided by the resistance. So now I can just do some math here. And we have a 12-volt battery. We have a resistor of 24 ohms. So that means that I have 0.5 amps in the circuit.
Now this is a pretty simple circuit, but what if we throw in another resistor, or 2, or 3, or 4?
Let's just put 1 in for now. We'll call that R2. Now we still have one closed loop, right? We still have current going through each of these circuit elements before they come back to the battery. So now my equation looks like this. VBAT minus the voltage at the resistor, that 24 ohm resistor, minus the voltage lost at resistor 2 is equal to 0, which means that the voltage of the battery is equal to the combined sum of the voltage lost at resistor, the 24 ohm resistor, and the voltage lost at resistor 2. Now, because they're in the same closed loop, there's no junctions, right? So the current is the same everywhere in that loop, which means the current through that 24 ohm resistor has to be the same as the current through that R2, which has to be the same as the voltage, the current going through that battery. So we would have VBAT is equal to I times that 24 ohm resistor plus I times whatever the value of R2 is. And then we could just plug in numbers again because we'd probably know what R2 was, and we could solve once again for current through this circuit. This is called a series circuit. Here is a parallel circuit, and in this case we're going to have to apply the junction rule and the loop law because I have current coming out of the battery, right, and it splits when I get up to this junction here, and so I get current in this branch, in this branch, in that branch. Remember what goes into the junction, so that's the current, I like to call that IBAT, the current coming out of the battery, has to equal the sum of these, right? What goes in must go out, and since it splits into 3 ways, and who knows what the magnitude, they could be the same if they're the same resistors in each of those branches, or they could be different, but they have to add up to the current in the battery. Well, since now I have different currents, what does my loop equation look like? Because remember, it's the voltage around a closed loop equals 0. So each of these resistors is in a separate loop. How do I know? Well, let's take a look. If I start my pen on, the positive terminal of the battery, and I move it all the way around, notice if I don't pick it up at all, that is a loop. That is a closed loop. So for my loop, we'll call this loop number 1. For loop number 1, the voltage at the battery minus the voltage at resistor 1 has to equal 0. Or voltage at the battery minus I1, we're going to call the current through R1 I1, times R1 has to equal 0. That's one closed loop. How do I know it's a closed loop? Because when I draw my pen all the way around, I never pick it up. Let's try another closed loop. So I'm going to start at the battery again, and this time I'm going to go through resistor 2. So I go through resistor 2, and there is my next closed loop. So that's loop number 2. So that means the voltage of the battery, right, that's where I started. Then I went through resistor 2. That voltage loss has to equal 0. So now my equation for that loop, that closed loop, is I2 times R2 equals 0. Well, resistor 3 doesn't have a line through it yet, so it must be in its own loop. So we're going to start out the battery again. This time I'm going to go all the way through R3 without picking my pen up. And that means I started the battery. I went through resistor 3, so I lost voltage at resistor 3, and that has to equal 0. So VBAT minus I3 R3 equals 0. So I have 3 closed loop because I have 3 branches. And the current in each of these branches could be different. If these resistor values are different, then the current value is different. But the one thing you should notice in common, is that the potential difference across those resistors, get rid of that, right? These have to be the same. The voltage of the battery minus the voltage at resistor 1 equals 0. The voltage of the battery minus the voltage of resistor 2 has to be 0. So that means that all these voltages have to be the same, even if the current's not the same in each branch, right? Because voltage is the current times the resistance. So if the resistors are different, the current's going to be different, but the voltage across them have to be the same. So the voltage across each resistor in parallel, I can spell, is equal in this case to the voltage of the battery because I just have a simple parallel circuit. So it's like I have 3 separate loops. It's like I have 3 wires that are totally independent of each other. The only thing that is affecting that is the fact that my battery now has to deliver 3 times the current it would have if I only had one resistor. And we will do another parallel circuit where we actually solve for values in class. The last type of circuit is a combination circuit. And in a combination circuit, we have a resistor in series, usually with the battery, and then we have resistors in parallel. So when we do this, we need to draw the path for current. So if we take a look, we see that current flows out of the battery and through R1. So we're going to call that I1, which is also equivalent to the current out of the battery. What I call I bat, and we hit this junction here and we split into I2 and into I3. So we have a junction, so we're going to have the junction rule, what comes in must go out. So that means that the current coming from the battery, or that I1, has to equal the sum of I2 plus I3. What goes in must come out. Now, when the current leaves the battery, it hits that junction, it goes through separate loops. So when we apply Kirchhoff's loop law, because we have a junction and we split into 2 different currents, we are going to have 2 different loop equations for this circuit. So when I draw my loop, we're going to put our pen down here at the top of the battery, and we're going to draw through R1, and we're going to hit this junction, and now we're going to go down to R2. So that is my first closed loop. So we'll call that loop 1. We gain voltage at the battery, right? That's where I started. We lose voltage across R1, and then we lose voltage across R2, and that has to equal 0 because I start at the battery, I go through R1, R2 before I get back, and the sum of those voltages have to equal 0. Now, when I write this with Ohm's law, we have to take into account the fact that I1 and I2 are different. So when I write this, it'll look like V bat minus I1 R1 minus I2 R2, and that equals 0, and I1 and I2 are different, right? Because I1 is what feeds the junction, and I2 is part of the current coming out of the junction, not all of it. For my second loop, so we've got one more loop here. If I put my pen down here at the battery, so we gain voltage at the battery, we go across R1 just like we did before, but now we're going to go across R3 and come all the way back. So this is another closed loop. So that's my second loop. So we're going to call that, so V bat, right? I start at the battery, I gain voltage at the battery, I lose voltage across resistor 1 just like I did with my first loop, minus the voltage lost at resistor 3 equals 0. And so if we want to plug in Ohm's law, we have voltage of the battery, which is always a given in a problem. That's why we don't put like I bat, R bat. I mean, there is resistance to the battery, but usually the voltage of the battery is given in the problem, minus I1 R1. God, what is going on with this thing today? V bat minus I1 R1 minus I3 R3 equals 0. Now, if we take a look at this, before we could solve the series circuit because the current was the same everywhere. And with parallel, when we had the separate branches, we didn't have a problem there. Even though the current split, the voltage across that resistor was the same as the battery. So solving a problem like that's not a big deal. But here, I have 3 things that are unknown. Current 1, the current coming out of the battery and going through R1, current 2 and current 3, but I only have 2 equations. Remember, in the beginning of the semester, we talked about if we have multiple unknowns, we need that many equations. So if I have 2 unknowns, I need 2 equations. Well, I have 3 unknowns. I need 3 equations. Well, guess what? We could use this as an equation. So we could replace I1 with I2 and I3, and I could do the same thing over here, replace I1 with I2 or I3, or I could rearrange this and solve for 1 and plug that in. So we can actually get down to 2 variables with our 2 equations and do simultaneous equations to find our current. But we'll save that for class. So you go to your WSQ. There's one multiple choice question. The other WSQ question, I want you to, now in your notes, I want you to write the loop equation for this series circuit, one loop, so the current is the same everywhere. And then I want to see if you can find the current that flows through the circuit. So the current that's coming out of that 12-volt battery and passing through the 400 and 290 ohm resistors. Remember, this is a series circuit. There's no junction, so the current is the same everywhere. So fill out your WSQ. We'll see how you do, and we'll talk about it in class. So I'll see you in class.